Hello everyone.
Hi everyone. Today we are continuing our implementation of MakeMore, our favorite character level language model. Now, you'll notice that the background behind me is different. That's because I am in Kyoto and it is awesome. So I'm in a hotel room here. Now, over the last few lectures, we've built up to this architecture that is a multi-layer perceptron character level language model. So we see that it receives 3 previous characters and tries to predict the 4th character in a sequence using a very simple multi-layer perceptron using one hidden layer of neurons with 10 nonlinearities. So what I'd like to do now in this lecture is I'd like to complexify this architecture. In particular, we would like to take more characters in a sequence as an input, not just 3. And in addition to that, we don't just want to feed them all into a single hidden layer because that squashes too much information too quickly. Instead, we would like to make a deeper model that squashes too much information. That we don't just want characters in a sequence as an input, not just 3. And in addition to that, we don't just want to feed them all into a single hidden layer because that squashes too much information too quickly. Instead, we would like to make a deeper model that progressively fuses this information to make its guess about the next character in a sequence. And so we'll see that as we make this architecture more complex, we're actually going to arrive at something that looks very much like a WaveNet. So WaveNet is this paper published by DeepMind in 2016. And it is also a language model, basically, but it tries to predict audio sequences instead of character level sequences or word level sequences. But fundamentally, the modeling setup is identical. It is an autoregressive model, and it tries to predict the next character in a sequence. And the architecture actually takes this interesting hierarchical sort of approach to predicting the next character in a sequence with this tree-like structure. And this is the architecture, and we're going to implement it in the course of this video. So let's get started. So the starter code for part 5 is very similar to where we ended up in part 3. Recall that part 4 was the manual backpropagation exercise that is kind of an aside. So we are coming back to part 3, copy-pasting chunks out of it, and that is our starter code for part 5. I've changed very few things otherwise. So a lot of this should look familiar to you if you've gone through part 3. So in particular, very briefly, we are doing imports. We are reading our data set of words, and we are processing the data set of words into individual examples, and none of this data generation code has changed. And basically, we have lots and lots of examples. In particular, we have 182,000 examples of 3 characters trying to predict the 4th one. And we've broken up every one of these words into little problems of given 3 characters, predict the 4th one. So this is our data set, and this is what we're trying to get the neural net to do. Now, in part 3, we started to develop our code around these layer modules that are, for example, like class linear. And we're doing this because we want to think of these modules as building blocks and like a Lego building block bricks that we can sort of like stack up into neural networks. And we can feed data between these layers and stack them up into sort of graphs. Now, we also developed these layers to have APIs and signatures very similar to those that are found in PyTorch. So we have torch.nn, and it's got all these layer building blocks that you would use in practice. And we were developing all of these to mimic the APIs of these. So for example, we have linear. So there will also be a torch.nn.linear, and its signature will be very similar to our signature, and the functionality will be also quite identical as far as I'm aware. So we have the linear layer, we have the Bashorm 1D layer, and the 10H layer that we developed previously. And linear just does a matrix multiply in the forward pass of this module. Bashorm, of course, is this crazy layer that we developed in the previous lecture. And what's crazy about it is, well, there's many things. Number one, it has these running mean and variances that are trained outside of backpropagation. They are trained using exponential moving average inside this layer when we call the forward pass. In addition to that, there's this training flag, because the behavior of Bashorm is different during train time and evaluation time. And so suddenly we have to be very careful that Bashorm is in its correct state, that it's in the evaluation state or training state. So that's something to now keep track of, something that sometimes introduces bugs. State and this training flag, because the behavior of Bashorm is different during train time and evaluation time. And so suddenly we have to be very careful that Bashorm is in its correct state, that it's in the evaluation state or training state. So that's something to now keep track of, something that sometimes introduces bugs. Because you forget to put it into the right mode. And finally, we saw that Bashorm couples the statistics or the activations across the examples in the batch. So normally we thought of the batch as just an efficiency thing. But now we are coupling the computation across batch.
Why he says that it's different? So this was during the training phases when we train these variables where it went. Yeah, these bn gain, bn draw, bn bias. But when we come to validation set or anything, right? We are not training these variables. We just take the overall batch mean and variance. Batch, I'm saying over whole of the data set, or universal mean and universal variance. There is no training of these variables like we were doing. So only in the training phase we back propagate and change these values. Apart from that, we're not changing any values in the batch normalization. That is true for all the variables, no? Okay, we'll see.
Elements, the examples in the batch. So statistics or the activations across the examples in the batch. So normally we thought of the batch as just an efficiency thing, but now we are coupling the computation across batch elements, and it's done for the purposes of controlling the activation statistics, as we saw in the previous video. So it's a very weird layer, at least a lot of bugs. Partly, for example, because you have to modulate the training and eval phase and so on. In addition, for example, you have to wait for the mean and the variance to settle and to actually reach a steady state. And so you have to make sure that basically there's state in this layer, and state is harmful, usually. Now, I brought out the generator object. Previously, we had a generator equals G and so on inside these layers. I've discarded that in favor of just initializing the torch RNG outside here using just once globally, just for simplicity. And then here we are starting to build out some of the neural network elements. This should look very familiar. We have our embedding table C, and then we have a list of layers. And it's a linear, feeds to batch neuron, feeds to 10H, and then a linear output layer, and its weights are scaled down, so we are not confidently wrong at initialization. We see that this is about 12,000 parameters. We're telling PyTorch that the parameters require gradients. The optimization is, as far as I'm aware, identical and should look very, very familiar. Nothing changed here. Loss function looks very crazy. We should probably fix this. And that's because 32 batch elements are too few. And so you can get very lucky or unlucky in any one of these batches, and it creates a very thick loss function. So we're going to fix that soon. Now, once we want to evaluate the trained neural network, we need to remember, because of the batch norm layers, to set all the layers to be training equals false. So this only matters for the batch norm layer so far. And then we evaluate. We see that currently we have a validation loss of 2.10, which is fairly good, but there's still ways to go. But even at 2.10, we see that when we sample from the model, we actually get relatively name-like results that do not exist in a training set. So for example, Ivan, Kilo, Pros, Alaya, etc. So certainly not reasonable, not unreasonable, I would say, but not amazing. And we can still push this validation loss even lower and get much better samples that are even more name-like. So let's improve this model now. Okay, first, let's fix this graph because it is daggers in my eyes and I just can't take it anymore. Which is
I've just tried to copy the code because here, right, the code that is there is, I think after the whole tutorial, right, the stage that it reaches, it is in that state. But initially, from the video itself, right? I try to make few changes. Specifically, changes are regarding this, how we were embedding and changing the view and then going through the layers and getting it. So mostly like that. So not much change, but so that we start with him where he is, we are also in the same state.
Which is fairly good, but there's still ways to go. But even at 2.10, we see that when we sample from the model, we actually get relatively name-like results that do not exist in a training set. So for example, Ivan, Kilo, Pros, Alaya, etc. So certainly not reasonable, not unreasonable, I would say, but not amazing. And we can still push this validation loss even lower and get much better samples that are even more name-like. So let's improve this model now. Okay, first, let's fix this graph because it is daggers in my eyes and I just can't take it anymore. So loci, if you recall, is a Python list of floats. So for example, the first 10 elements look like this. Now, what we'd like to do basically is we need to average up some of these values to get a more sort of representative value along the way. So one way to do this is the following. In PyTorch, if I create, for example, a tensor of the first 10 numbers, then this is currently a one-dimensional array. But recall that I can view this array as two-dimensional. So for example, I can view it as a 2x5 array, and this is a 2D tensor now, 2x5. And you see what PyTorch has done is that the first row of this tensor is the first 5 elements, and the second row is the second 5 elements. I can also view it as a 5x2 as an example. And then recall that I can also use -1 in place of one of these numbers. And PyTorch will calculate what that number must be in order to make the number of elements work out. So this can be like this or like that.
Thing I want to validate is what happens when we give, means both should be multiplied to 10, right? If I don't give like that, while this trains, right? I just want to see. If comma 2 is this, what happens if I give this as 3m? So the multiple of these, right? So you can say 1 cross 10 works, 2 cross 5 works, 3 cross 4 doesn't work, means with 3 we can't do it. So 3, 4 also doesn't work, then 5 cross 2, same thing. Right, so like this, it can be multiple. So either it can, this value, right, can be 2, 5, 10, 1, something like this, nothing else.
Both will work. Of course, this would not work. Okay, so this allows us to spread out some of the consecutive values into rows. So that's very helpful because what we can do now is, first of all, we're going to create a torch.tensor out of a list of floats. And then we're going to view it as whatever it is, but we're going to stretch it out into rows of 1,000 consecutive elements. So the shape of this now becomes 200 by 1,000. And each row is 1,000 consecutive elements in this list. So that's very helpful because now we can do a mean along the rows. And the shape of this will just be 200. And so we've taken basically the mean on every row. So plt.plot of that should be something nicer. Much better.
Hmm. It is still running.
So we see that we've basically made a lot of progress. And then here, this is the learning rate decay. So here we see that the learning rate decay subtracted a ton of energy out of the system and allowed us to settle into sort of the local minimum in this optimization. So this is a much nicer plot. Let me come up and delete the monster, and we're going to be using this going forward. Now, next up, what I'm bothered by is that you see our forward pass is a little bit gnarly and takes way too many lines of code. So in particular, we see that we've organized some of the layers inside the layers list, but not all of them for no reason. So in particular, we see that we still have the embedding table special cased outside of the layers. And in addition to that, the viewing operation here is also outside of our layers. So let's create layers for these, and then we can add those layers to just our list. So in particular, the two things that we need is here, we have this embedding table, and we are indexing at the integers inside the batch XB, inside the tensor XB. So that's an embedding table lookup just done with indexing. And then here we see that we have this view operation, which if you recall from the previous video, simply rearranges the character embeddings and stretches them out into a row. And effectively what that does is the concatenation operation, basically, except it's free because viewing is very cheap in PyTorch. And no memory is being copied. We're just re-representing how we view that tensor. So let's create modules for both of these operations, the embedding operation and the flattening operation. So I actually wrote the code in just to save some time. So we have a module embedding and a module flatten, and both of them simply do the indexing operation.
Embedding and is the next class. That is for this, right? Okay. So during initialization, this is how we are going to initialize. Okay. Got it. For all the layers he's doing, every layer has a training, this thing is there. Might create a variable of its own itself. Mm. Cross entropy. Okay, okay. This is outputting an X here. It's the input. Okay, it's running. And there's something that defines this. So embedding, right? Two things. One, here the initialization happens, and the next thing is during the training we use this. So he's saying just do this here. Number of embeddings is the embedding dimension. What is the size of each? Yeah, it should be.
And we evaluate. We see that currently we have flatten.
Okay, for the time being, I will do it. Later, we'll see why we need it. Flatten. Only thing I see is initializing with this embedding. But there is no initialization itself here. Okay, nice. -1 and 1 is for the parameters. Let's give this name as so this will these weights. What is this weight here? Why we are taking this weight is a question for me as a parameter, because we are not training these weights, right? We were doing embedding here, so this will get replaced with um embedding and this thing, and that will be C. Okay, here it is, the parameter that is coming inside parameters as. So the reason we are sending this as, it should not be called as a weights or something, but these are the inputs that are going, right? The embedding. So unless we put them in parameters, their values won't get changed, and the purpose of whole training itself will go off, right? Because if you remember, these are the inputs that are going into the, so 3 words, embeddings of each word, and when we are back propagating, we are changing the values here as well. So that's what is the main crux of it, right? To use this weights. That's weights and the parameters. And this has no parameters.
And both of them simply do the indexing operation in a forward pass and the flattening operation here. And this C now will just become a self.weight inside an embedding module. And I'm calling these layers specifically embedding and flatten because it turns out that both of them actually exist in PyTorch. So in PyTorch, we have nn.embedding, and it also takes the number of embeddings and the dimensionality of the embedding, just like we have here. But in addition, PyTorch takes a lot of other keyword arguments that we are not using for our purposes yet. And for flatten, that also exists in PyTorch. And it also takes additional keyword arguments that we are not using. So we have a very simple flatten. But both of them exist in PyTorch. They're just a bit more simpler. And now that we have these, we can simply take out some of these special cased.
Oh, we can define embedding here itself, is it? So once that gets initialized, so this will take care of its own now because embedding is a layer itself now. Weights, where is weight? Okay, it's only it has been initialized. Here, right? Pass on the X. Yep, we pass, sorry. So pass on the X and we, so this is what is expected out of it. We need to call this XB. Sorry, not here. We just need to pass embeddings. It will do the flat. No. So first is the embedding layer, and then we have something known as a flattening layer as well. So after this, right, flatten as well. So first embedding happens, then flattening happens. Okay, and that's where, so first we pass, first this gets called from the embedding, it pulls up those things, and then the flattening gets called. So it should be MB should be XP. Why? First layer will be this layer, okay, which has been already initialized. So XP will come here. From the XP will pull out all those required embeddings, the 3 embeddings for each of these words, whatever be the size, embeddings of these words. Then that will call this, which will flatten this and send it out. It will again get stored in X, and then it will move in. So these all are Not required. That should itself do it. But let's see.
Things. So instead of C, we're just going to have an embedding and a vocab size and n embed. And then after the embedding, we are going to flatten.
Yeah, that
So let's construct those modules. And now I can take out this C. And here I don't have to special case it anymore because now C is the embedding's weight and it's inside layers. So this should just work. And then here, our forward pass simplifies substantially because we don't need to do these now outside of these layers, outside and explicitly. They're now inside layers, so we can delete those. But now to kick things off, we want this little x, which in the beginning is just xb, the tensor of integers.
XP is anyway not changing. I'm not sure if that has any impact on it. Oh, very sure. Need to check on this one.
Specifying the identities of these characters at the input. And so these characters can now directly feed into the first layer, and this should just work. So let me come here and insert a break, because I just want to make sure that the first iteration of this runs and that there's no mistake.
True.
So that ran properly. And basically, we've substantially simplified the forward pass here. Okay, I'm sorry, I changed my microphone, so hopefully the audio is a little bit better. Now, one more thing that I would like to do in order to PyTorchify our code even further is that right now we are maintaining all of our modules in a naked list of layers. And we can also simplify this because we can introduce the concept of PyTorch containers. So in torch.nn, which we are basically rebuilding from scratch here, there's a concept of containers. And these containers are basically a way of organizing layers into lists or dicts and so on. So in particular, there's a sequential, which maintains a list of layers and is a module class in PyTorch. And it basically just passes a given input through all the layers sequentially, exactly as we are doing here. So let's write our own sequential. I've written a code here. And basically the code for sequential is quite straightforward. We pass in a list of layers, which we keep here, and then given any input in a forward pass, we just call all the layers sequentially and return the result. And in terms of the
So it's putting all of the things there. So this will be implemented here. Just now, this will be self-dot layers rather than layers, and this is what we want to implement there, where when we call this, it runs them one by one. So what's happening for layers? For layer in self.layer, we are calling layer dot x. The reason we do this right should be create another object, but I'm not sure. And then this parameters as well, I guess, right? So when you call sequential dot parameter, it should give you all the parameters as well. Should work. And then so I pass on these layers. It parameters equal to model dot parameters, and then here while training should be model x.
Parameters is just all the parameters of the child modules. So we can run this, and we can again simplify this substantially. Because we don't maintain this naked list of layers, we now have a notion of a model, which is a module, and in particular is a sequential of all these layers. And now parameters are simply just model.parameters. And so that list comprehension now lives here. And then here we are doing all the things we used to do. Now here, the code again simplifies substantially, because we don't have to do this forwarding here. Instead, we just call the model on the input data. And the input data here are the integers inside xb. So we can simply do logits, which are the outputs of our model, are simply the model called on xb. And then the cross entropy here takes the logits and the targets. So this simplifies substantially. And then this looks good. So let's just make sure this runs. That looks good. Now here, we actually have some work to do still here, but I'm going to come back later. For now, there's no more layers. There's a model.layers, but it's naughty to access attributes of these classes directly. So we'll come back and fix this later. And then
Logits. Okay, because it has been trained only one side, so the error is huge because we broke here, right? Should have run multiple times.
here, of course, this simplifies substantially as well because logits are the model called on X, and then these logits come here. So we can evaluate the train and validation loss, which currently is terrible because we just initialized the neural net. And then we can also sample from the model, and this simplifies dramatically as well because we just want to call the model onto the context and outcome logits. And then these logits go into softmax and get the probabilities, etc. So we can sample from this model. What did I screw up? Okay, so I fixed the issue and we now get the result that we expect, which is gibberish because the model is not trained because we reinitialize it from scratch. The problem was that when I fixed this cell to be model.layers instead of just layers, I did not actually run the cell. And so our neural net was in a training mode, And what caused the issue here is the batch norm layer, as batch norm layer often likes to do, because batch norm was in the training mode, and here we are passing in an input, which is a batch of just a single example made up of the context. And so if you are trying to pass in a single example into a batch norm that is in the training mode, you're going to end up estimating the variance using the input, and the variance of a single number is not a number, because it is a measure of a spread. So for example, the variance of just a single number 5, you can see is not a number. And so that's what happened, and batch norm basically caused an issue, and then that polluted all of the further processing. So all that we had to do was make sure that this run.
Mm. It will keep tracking the running mean and variance so that during the inference we use this.
And we basically made the issue of, again, we didn't actually see the issue with the loss. We could have evaluated the loss, but we got the wrong result because batch norm was in the training mode. And so we still get a result, it's just the wrong result because it's using the sample statistics of the batch. Whereas we want to use the running mean and running variance inside the batch norm. And so, again, an example of introducing a bug inline because we did not properly maintain the state of what is training or not. Okay, so I rewritten everything, and here's where we are. As a reminder, we have the training loss of 2.05 and validation of 2.10. Now, because these losses are very similar to each other, we have a sense that we are not overfitting too much on this task, and we can make additional progress in our performance by scaling up the size of the neural network and making everything bigger and deeper. Now, currently we are using this architecture here, where we are taking in some number of characters, going into a single hidden layer, and then going to the prediction of the next character. The problem here is we don't have a naive way of making this bigger in a productive way. We could, of course, use our layers, sort of building blocks and materials, to introduce additional layers here and make the network deeper, but it is still the case that we are crushing all of the characters into a single layer all the way at the beginning. And even if we make this a bigger layer and add neurons, it's still kind of like silly to squash all that information so fast in a single step. So what we'd like to do instead is we'd like our network to look a lot more like this in the WaveNet case. So you see in the WaveNet, when we are trying to make the prediction for the next character in the sequence, it is a function of the previous characters that feed in, but not all of these different characters are not just crushed to a single layer and then you have a sandwich. They are crushed slowly. So in particular, we take two characters and we fuse them into sort of like a bigram representation. And we do that for all these characters consecutively. And then we take the bigrams and we fuse those into 4 character level chunks. And then we fuse that again. And so we do that in this like tree-like hierarchical manner. So we fuse the information from the previous context slowly into the network as it gets deeper. And so this is the kind of architecture that we want to implement. Now, in the WaveNet's case, this is a visualization of a stack of dilated causal convolution layers. And this makes it sound very scary, but actually the idea is very simple. And the fact that it's a dilated causal convolution layer is really just an implementation detail to make everything fast. We're going to see that later. But for now, let's just keep the basic idea of it, which is this progressive fusion. So we want to make the network deeper, and at each level, we want to fuse only 2 consecutive elements. 2 characters, then 2 bigrams, then 2 foregrams, and so on. So let's implement this. Okay, so first up, let me scroll to where we built the dataset, and let's change the block size from 3 to 8. So we're going to be taking 8 characters of context to predict the 9th character. So the dataset now looks like this. We have a little.
This is already done up. So we are taking 8 characters here.
A lot more context feeding in to predict any next character in a sequence. And these 8 characters are going to be processed in this tree-like structure. Now, if we scroll here, everything here should just be able to work. So we should be able to redefine the network. You see that the number of parameters has increased by 10,000, and that's because the block size has grown. So this first linear layer is much, much bigger. Our linear layer now takes 8 characters into this middle layer. So there's a lot more parameters there. But this should just run. Let me just break right after the very first iteration. So you see that this runs just fine. It's just that this network doesn't make too much sense. We're crushing way too much information way too fast. So let's now come in and see how we could try to implement the hierarchical scheme. Now, before we dive into the detail of the re-implementation here, I was just curious to actually run it and see where we are in terms of the baseline performance of just lazily scaling up the context length. So I'll let it run, we get a nice loss curve, and then evaluating the loss, we actually see quite a bit of improvement just from increasing the context length. So I started a little bit of a performance log here, and previously where we were is we were getting a performance of 2.10 on the validation loss, and now simply scaling up the context length from 3 to 8 gives us a performance of 2.02. So quite a bit of an improvement here. And also when you sample from the model, you see that the names are definitely improving qualitatively as well. So we could of course spend a lot of time here tuning things and making it even bigger and scaling up the network further, even with the simple sort of setup here. But let's continue and let's implement a hierarchical model and treat this as just a rough baseline performance. But there's a lot of optimization left on the table in terms of some of the hyperparameters that you're hopefully getting a sense of now. Okay, so let's scroll up now and come back up. And what I've done here is I've created a bit of a scratch space for us to just look at the forward pass of the neural net and inspect the shape of the tensors along the way as the neural net forwards. So here, I'm just temporarily for debugging, creating a batch of just say 4 examples. So 4 random integers. Then I'm plucking out those rows from our training. Set. And then I'm passing into the model the input XB. Now the shape of XB here, because we have only 4 examples, is 4 by 8. And this 8 is now the current block size. So inspecting XB, we just see that we have 4 examples. Each one of them is a row of XB. And we have 8 characters here. And this integer tensor just contains the identities of those characters. So the first layer of our neural net is the embedding layer. So passing XB, this integer tensor, through the embedding layer creates an output that is 4 by 8 by 10. So our embedding table has, for each character, a 10-dimensional vector that we are trying to learn. And so what the embedding layer does here is it plucks out the embedding vector for each one of these integers and organizes it all in a 4 by 8 by 10 tensor now. So all of these integers are translated into 10-dimensional vectors inside this 3-dimensional tensor now. Now passing that through the flattened layer, as you recall, what this does is it views this tensor as just a 4 by 80 tensor. And what that effectively does is that all these 10-dimensional embeddings for all of these 8 characters just end up being stretched out into a long row. And that looks kind of like a concatenation operation, basically. So by viewing the tensor differently, we now have a 4 by 80, and inside this 80, it's all the 10-dimensional vectors just concatenate next to each other. And then the linear layer, of course, takes 80 and creates 200 channels just via matrix multiplication. So far, so good. Now I'd like to show you something surprising. Let's look at the insides of the linear layer and remind ourselves how it works. The linear layer here in the forward pass takes the input x, multiplies it with a weight, and then optionally adds bias. And the weight here is two-dimensional, as defined here, and the bias is one-dimensional here. So effectively, in terms of the shapes involved, what's happening inside this linear layer looks like this right now. And I'm using random numbers here, but I'm just illustrating the shapes and what happens. Basically, a 4x80 input comes into the linear layer, gets multiplied by this 80x200 weight matrix inside, and then there's a plus 200 bias. And the shape of the whole thing that comes out of the linear layer is 4x200, as we see here. Now, notice here, by the way, that this here will create a 4x200 tensor, and then plus 200, there's a broadcasting happening here, but 4x200 broadcasts with 200, so everything works here. So now the surprising thing that I'd like to show you that you may not expect is that this input here that is being multiplied doesn't actually have to be two-dimensional. This matrix multiply operator in PyTorch is quite powerful, and in fact you can actually pass in higher dimensional arrays or tensors and everything works fine. So for example, this could be 4x5x80, and the result in that case will become 4x5x200. You can add as many dimensions as you like on the left here. And so effectively what's happening is that the matrix multiplication only works on the last dimension, and the dimensions before it in the input tensor are left unchanged.
Okay. We'll see in the next video afterwards. It's already more of a time.